Welcome to the amazing world of regression. Regression analysis is a powerful statistical tool used to explore the relationship between variables. The three main types of regression include linear regression, which is used for continuous outcomes, logistic regression, which is for categorical outcomes, and Cox regression, also known as survival analysis, is for time to event outcomes. In health research, we typically think in terms of exposures, which are the factors that may cause change, or outcomes, which are the results or effects. However, when using statistical softwares or reading scientific literature, these variables are often referred to using more formal terminologies. For example, for exposures, we often use the equivalent term predictor variable or explanatory variable or independent variable. And for outcomes, we use response variable or dependent variable. Coming back to the regression topic, let's discuss why regression is so powerful. Regression can quantify relationships, measuring the strength and direction of relationship between predictor and outcomes. It can even predict outcomes, estimating the expected value of the outcome based on predictor variables. And finally, it can adjust for covariates, controlling for confounding variables and isolating the true effect of the predictors. In this chapter, we will focus on linear regression. In the next chapter, we'll cover logistic regression and Cox regression. Linear regression is a statistical method used to model and analyze the relationship between a continuous outcome variable, such as, say, height, weight, systolic blood pressure, etc., and one or more explanatory or what we call the independent variables, such as BMI, sex, or smoking status. There are two types of linear regressions, simple and multiple. In simple linear regression, we have only one predictor, while in multiple linear regression, we will have two or more predictors. The equation for simple linear regression looks like this. We will discuss more about this in the next few slides. And the equation for multiple linear regression is obviously a little bit more complex, like the one you see on your screen. The example for simple linear regression is you might like to predict systolic blood pressure based on just one predictor, that is BMI. In case of multiple linear regression, we might like to predict the same systolic blood pressure based on multiple predictors like BMI, sex, or age. Let's consider this research question. Is there an association between our one predictor, that is BMI, and the systolic blood pressure, our continuous variable outcome of interest? In this case, our hypothesis would be, the null hypothesis would be that there is no association, that is, the slope beta 1 will be 0. What it means is that as if you see here, as the BMI is increasing, there is no change in the systolic blood pressure. The systolic blood pressure of the person with 20 BMI or 25 BMI or 35 BMI or 50 BMI, all are the same. So there is a flat line. So the slope is literally 0. The alternative hypothesis is that there is an association between our exposure and outcome. So the slope of beta 1 is not 0, and it would look like something like this. As the BMI is increasing, we see that there is an increase in the systolic blood pressure. The person with say 20 BMI has a lower systolic blood pressure compared to the one with BMI 30 and so on. More on that in the coming slides. And if the slow beta 1 is statistically significant, we reject the null hypothesis and conclude that BMI does impact systolic blood pressure.